through the body is not possible, but it should be around the body. In this table, you can see the properties of the body at 2.4 gigahertz, which will be the communication frequency for skin, fat, and muscle tissues. And you can see that, in general, the permittivity is very high, and these tissues also have very high losses. In order to assess these properties, we designed two different antennas, which are very commonly used. The one on the left is a F antenna with a coplanar waveguide feed, which is implemented using one metal layer over a substrate. On the right side, you have a patch antenna, which is made with two metal layers, and this is a very typical topology, which is used in many systems, as some wearable systems we saw yesterday. In this case, we used a substrate with 1.6 millimeter thickness, 3.1 permittivity, and a medium-high loss tangent of 0.01. I will show you some simulated results obtained with Ansoft HFSS electromagnetic simulator. The first of them is the matching, which is the matching of the antenna to a 50 ohm line. So normally we consider that the antenna is matched to the line when the reflected power is less than 10%. It means that the S11 parameter is below minus 10 dB. You can see that for the patch antenna, it doesn't matter if the patch is in free space or on the body, the matching is still okay at 2.4 gigahertz. However, for the F antenna, it happens in free space, the matching is good, but when placed on the body, it is completely mismatched at 2.4, and it has a new resonance at 1.5 gigahertz due to the high permittivity of the body tissues. We also check the radiation efficiency, which means what happens to this power after reflecting due to mismatch. And we saw that the efficiency of the F antenna decreases from 97 to 4% due to the body effect. However, for the patch antenna, due to the second metal layer, the efficiency decreases only to only 20%. We also check the directivity, which means how this power after mismatch and efficiency gets distributed in the 3D space. We made two cuts, which are two planes perpendicular to the body. And you can see here, which is the gain, the directivity in dB in the vertical axis, and the horizontal axis represents the elevation angle. This means that 0 degree means radiation out of the body, 90 degree or minus 90 parallel to the body, 180 inside the body. If you focus on the solid lines, which means free space operation, you can see that the patch antenna is a bit directional. However, the if antenna is showing the typical monopole type of radiation, which is omnidirectional in the H plane, and it has nulls, very heavy nulls at 90 degrees for the E plane. That's for free space. When we place them on the body, which are the dashed lines, you can see that the patch is still maintaining the properties. However, the if antenna is changing a lot the radiation diagram in the E plane. We also checked the effect of increasing the air gap or leaving some space between the body and the F antenna, the one-layer antenna. So you can see that the efficiency is increasing and the matching to the line starts to improve also. So we could say that for 4 millimeters, in the operation bandwidth of 2.4 gigahertz, we have reasonable good match. However, for 4 millimeters, the efficiency is still 20%. This means that we should increase the distance, and then the solution becomes less compact. In order to confirm these simulations, we made also some measurements with commercial antennas. We selected a printed monopole and a PFA with a ground plane. You can see in this graph that the PFA is not detuned by the body. However, the printed monopole is detuned, which confirms the simulations. So conclusion, we can say that the effect of the body on antennas is impedance mismatch, efficiency drop, and radiation pattern distortion. We also have seen that an additional metal layer reduces body effect because of suppression of back radiation, but this makes the antenna more directive. And we also saw that a smaller gap improves the performance on one-layer antennas. For the present solution, for the mobile sensor node, The small size was a big requirement, so a ceramic antenna by Johansson Technologies was selected, which is the one you can see in these circles. In the mobile sensor node, the distance to the body is 5 millimeters, which should improve the performance. However, in the first field test, the blocking effect of the body has been observed. That is that the radiation doesn't go through the body. The third important issue for the sensor node is the mobility. In general, in a mesh network, to keep the mesh operation, it requires devices to listen to the traffic to know if they need to operate as routers or not. And this is not feasible for battery-powered devices. For this kind of devices, normally father-to-child relations are created with some routing nodes. But this is not optimal if the child device, the end device, is moving frequently. So the solution in this system, the chosen solution has been to make the mobile device child for all the routing devices in the network.
2 more minutes.
Yep. So I will describe briefly the two applications based on this infrastructure. The first one is a device with a panic button and a location wrist, which contains a mobile sensor node and is sending frames every 2 seconds, and it also has a panic button. It's complemented by a fixed network on the house, and which routes the data to a central coordinator, which has some user location algorithms to detect if the user is staying too long in some room, for example. In that case, it will send a GSM message to some relative, and it will be possible to speak to the patient with a hands-free system located in the fixed network. The second application was developed, it's a sleep disorders monitoring system developed within the Sensation FP6 project, and it's made of body sensors for ECG and respiration rate, which are locked to some sensor communication modules, which send all the information to a central unit, which is a personal data processing unit. Currently, these SCM modules are being converted to mobile sensor nodes. So as a conclusion, a wireless sensor network infrastructure has been developed for personal monitoring, taking into account a small size, low power consumption, antenna body interaction, and mobility. For the antenna body interaction, we have seen the trade-off between directivity and efficiency. It's possible to further characterize the device for a specific location or platform, and we also saw the blocking effect of the body, which could be solved with some diversity system with 2 antennas on the 2 sides of the body. Future work also includes power line communications and ultra-wideband for this network. So I would like to explain a little bit that this system was developed by TSB Solutions in cooperation with Ikerlan Research Institute, and the antenna work has been done by Ikerlan in cooperation with IMEC and CEIT. I also encourage you to visit the stand of TSB Solutions at the hall, where you can see these prototypes. And you can also visit the stand of Ikerlan, where you can see more activities on healthcare from Ikerlan, and also our spin-off company called Microliquid.